Welcome to the radar grid, everyone. I am your tower director for today's explainer, and right now we have a very serious, highly critical situation unfolding in our airspace. We are currently tracking a notoriously difficult, incoming heavy. What is it? It's Cambridge Mathematics 9709, specifically Topic 2.2. We're talking about logarithmic and exponential functions, e to the x and the natural log of x. Now, as an elite Cambridge exam tower director, it is my absolute priority to guide you safely through the extreme, suffocating time pressure of the exam hall. We are going to prioritize your high-yield method marks, and we are going to ensure this incredibly dense mathematical problem touches down safely on the runway. Imagine you are sitting at that desk. The altimeter is spinning, the timer has officially started, and your exam paper is cleared for approach. The pressure is on. Are you ready to take control?
Okay, let's dive into this flashing amber warning we're getting right now. According to the principal examiner reports, which, if you think about it, are basically the ultimate black box flight recordings of past exam seasons, Topic 2.2 is consistently flagged. It is known as one of the most fundamentally misunderstood areas on the entire syllabus. Every single year, candidates across all tiers look at an equation involving Euler's number or a natural logarithm, and what happens? Their stress levels absolutely spike, and their analytical systems just shut down completely. It's a system failure. When panic sets in under that time pressure, students completely lose sight of their theoretical foundations. They start misinterpreting complex texts, they drop those absolutely crucial method marks left and right, and ultimately, their overall grade just plummets. But listen, today we are going to fix that. We are going to decode exactly what the examiners are looking for, so you never crash on this topic again.
To manage this crisis, here is our flight approach manifest. First up, radar grid initialization. Second, routing the approach vector. Third, clearing exam runway debris. And finally, the safe touchdown sequence. Let's get moving. Moving right into our first phase, radar grid initialization. It is time to identify exactly what kind of operator you are.
Think about it. When you sit down in that exam hall, you are essentially the radar operator. You're the one making the split-second decisions. But under extreme time pressure, candidates almost always mutate into one of two archetypical operators. Identifying which one you naturally default to is the very first step to securing your airspace. First up, we have router Alex. Now, Alex is meticulous, but Alex gets entirely bogged down in the minor details. Imagine this. Alex will stare at an e to the x substitution for 10 whole minutes, second-guessing every single variable and completely ignoring the required presentation format. What Alex is doing is effectively creating an infinite holding pattern. The exam clock is relentlessly ticking away, but Alex is stuck circling the exact same piece of algebra, paralyzing the entire sequence. Then, on the flip side, we have router Sam. Sam is the total opposite. Sam clears arguments for landing way too fast, without verifying the actual mathematical laws or structural safety regulations. Sam rushes through all the procedural steps, fundamentally confuses cause and effect, and entirely skips the explicit working out. Both Alex and Sam are going to crash their grades today. Why? Because they are letting the immense pressure of the exam hall dictate their methodology, rather than relying on their trained standard operating procedures. We need to find that perfect middle ground.
That brings us to Phase 2, routing the approach vector. We need to review our core flight principles. To safely route this mathematical approach and actually secure those vital method marks, we must deeply, fundamentally understand the syllabus. You see, the examiner isn't just looking for your final destination. They aren't just checking the bottom line for the correct answer. They are meticulously grading your entire flight path. This is the core of the method mark strategy, where points are generously awarded for the process, the working out, and the logical steps you took to get there. Notice how the inverse relationship between exponential functions, e to the x, and natural logarithms, the natural log of x, isn't just some basic calculator rule you can take for granted. As the syllabus defines it, this relationship is the core theoretical architecture required to truly understand causal relationships in higher mathematics. Think of them as mathematical mirrors of each other. E to the x and the natural log of x literally undo one another. When you have a crucial variable trapped way up high in an exponent, the natural log is your exact tool, your key, to bringing it safely down to the runway so you can solve for it. Understanding this precise definition, deep in your bones, allows you to manipulate incredibly complex equations under intense pressure without ever second-guessing your fundamental altitude. It grounds you. Now, we're looking at a detailed breakdown of the exact syllabus assessment objectives you are being tested on. It's broken into 3 distinct columns: knowledge and understanding, application, and analysis. You need to realize that top-performing students achieve significantly higher marks because they absolutely do not just solve the equation in a vacuum. They don't just crunch numbers. They reference cross-topic connections, they understand how logarithms apply to integration, how they weave into differentiation, and how they are used for modeling real-world exponential decay. They demonstrate a deep conceptual understanding that effortlessly transfers to completely unfamiliar contexts. Let's say you're mid-paragraph in an extended mathematical response or a complex proof, and suddenly you hit a massive structural block. Your brain freezes. Don't panic. This is where you deploy your formatting templates, systematically hitting knowledge, then application, and then analysis, step by step, to gently guide your sentence and your logic right back onto the correct glide slope.
Tower transmission check. Before we clear this response for touchdown, ensure your transponder is updated. Subscribe to Ace the Exams right now. That's at Ace the Exams, and turn on all notifications. Okay, our sensors are picking up a problem. Phase 3, clearing exam runway debris. We have to clear these examiner warnings immediately.
We have massive, dangerous debris on the runway right now in the form of actual, documented examiner warnings. These aren't guesses, these are the specific, recurring mistakes that the principal examiners see year after year, paper after paper. We absolutely cannot land this problem safely until we clear them out of the way. The principal examiner reports have identified exactly 3 major threats when dealing with exponential and logarithmic functions. Let's break them down. Threat 1. Candidates consistently confuse cause and effect. What does that mean? It means they mix up independent and dependent variables when they are dealing with growth or decay models. They don't know what is driving the change. Threat 2. Forgetting to check format and presentation. This is a heartbreaker. You do all the incredibly hard algebraic heavy lifting, but then you leave your final answer as an unsimplified fraction, or you simply don't use the required exact form that the question explicitly asked for. Boom, you drop the final marks. Threat 3. Failing to provide context-specific answers. The math you did might be technically algebraically correct, but if the specific question is about biological population growth, a negative answer makes zero physical sense. You can't have a negative number of bacteria. You absolutely have to interpret the data you've calculated and apply it to the real world.
And this brilliantly illustrates our next major hurdle. We have a direct quote pulled straight from the source data, and it highlights a truly critical error. It reads, "Examiner alert, candidates consistently confuse key terminology. Always define terms before using them in extended responses." This is exactly why you must establish precise definitions before you even think about initiating complex calculations. Let's be real, if you just start throwing around the natural log of x and e to the x without clearly defining your substitution variables, like for example explicitly stating let u equal e to the x to solve a hidden quadratic equation, the examiner simply cannot follow your logic. They aren't mind readers. To fix this mid-paragraph structural block, deploy a formatting template, like the Peel method adapted for math. Make your point, show your evidence or equation, explain the substitution, and link it back to the solution. If the examiner can't seamlessly follow your logic, your method marks instantly evaporate, and your overall grade is going to crash hard.
All right, the runway is finally clear of debris. We are now entering Phase 4, the safe touchdown sequence and procedural framework.
Listen up, because this is the precise technical methodology that will guide your equations safely back onto the glide slope. This is how you lock in those high-yield method marks, no matter how much your hands are shaking or how much the clock is ticking in that exam hall. Let's initiate an interactive runway workshop right here, right now, using the deconstruct, solve, evaluate framework. I want you to imagine a 60-second visual timer ticking down. The pressure is on. Step 1. Identify the given information. When you look at a complex text data map or a terrifying word problem, your first move is to isolate the primary trend variable. Is it an EDDX growth curve? Find it. Step 2. Break it into logical steps. Do not be Router Alex. Don't just stare at the paper in an infinite holding pattern. Write down your inverse relationship rule immediately upon identifying the function. Step 3. Solve systematically. We need crystal clear working out, line by sequential line. Step 4. Check for reasonableness. This is where we look for debris on the runway again. Imagine a sample answer where a stressed student calculates time as -3 seconds using a logarithm. That completely violates the mathematical and logical safety rules. Time cannot be negative in this physical context. You absolutely must evaluate the limitations of the evidence and the assumptions you've made.
Finally, to log a successful, flawless, full-mark landing sequence, you must fiercely adhere to strict formatting conventions. We are talking about proper headings, the absolute correct mathematical terminology, appropriate final formats, and crystal clear annotation.
So the crucial point is this. Practical application actually requires these strict conventions to properly evaluate your performance. It's how you impress the examiner. If you use appropriate comparative connectives in an analysis question, or if you explicitly and clearly show exactly where you applied the natural logarithm to both sides of the equation, you are spoon-feeding the examiner exactly what they need to effortlessly award you maximum points. Think of this as your fuel-to-mark budget formula. The clearer your annotations, the more method marks you bank in your reserves. Our friends Router Alex and Router Sam have finally integrated these exact protocols into their systems, and guess what? They've just landed a perfect full-mark response.
And that brings us to the successful end of our simulation today. Your transponder is fully updated, you have internalized the actual examiner reports, and you now intimately know the inverse relationship theoretical architecture. So I leave you with this final critical thought. When that timer officially starts in the exam hall, will you decisively control the airspace, or will you let the equations control you? You have the complete system now to overcome that exam anxiety and absolutely dominate the paper. Before you go, make sure you subscribe to Ace the Exams. That's at Ace the Exams. Enable that notification bell so you never miss a briefing, and leave a comment down below sharing exactly which past paper gives you the most anxiety. Let us know, and we will queue it up for a future flight path. Until then, keep your vectors clear, trust your instruments, and I'll see you in the next explainer.